Thank you very much. Thank you everybody for coming to this conference, joining this session, optimizing SQL Server Data Warehouse. I am Dejan Sarka. I am working in this area nearly 40 years. Basically, I'm a mathematician, statistician, and also dealing with databases with SQL Server from 1992 from versions 4.2, and I co-authored 20 books so far, many courses, and so on. And I will talk a little bit about optimization of a data warehouse in SQL Server. First, in introduction, I will talk why would you do this. And then we'll talk about special indexes. They are not so well known, like filtered indexes, indexed views. Then about data compression, writing efficient queries. We'll analyze columnar storage, talk how you can update it, and what is the influence of column cardinality on the compression, on row compression, page compression, columnar compression. If we look at the whole picture, when you optimize a BI solution end-to-end, you must start with optimizing the way how you extract data from data sources, store it in staging area, then going through data warehouse to Power BI reports, data model, semantic model, and reports. So I will talk today about optimizing a data warehouse. Before I start with concrete options, so why would you do this? Well, in general, if you are using, let's say, import mode in Power BI, then typically you don't need to work so much on optimizing a data warehouse. Still, you might do a lot of reports and maybe some additional, more advanced data science analytics in data warehouse. And you might even decide, besides Transact-SQL queries, that you will also use a DirectQuery model in your Power BI reports. So then Power BI will send a lot of queries to your data warehouse. Then optimizing a data warehouse is really, really crucial. And optimizing means properly, of course, starting with proper model, but I'm not talking about this in this presentation, star schema and so on. I think Markus Aaron Miller Jensen already talked about this in the other track today. So I'm talking about not logical but physical optimizations. We all know classical indexes, balanced tree indexes, clustered, non-clustered indexes. Now I will start with some special indices. So first, not so well known, but could be very useful, not just in a data warehousing scenario, but also in a transactional scenario, are filtered indexes. These are non-clustered balanced trees where you include where clause in the create index statement. So you are indexing just part of the data. This makes a lot of sense when your distribution of data values is not really close to uniform. So some values are very frequent, very dense, some values are extremely rare. And then it makes sense to use index 6 on those rare values and scans on values that are not rare. So by filtering only those rare values, you are making a very efficient filtered index, efficient in a way that since these values are rare, also the index is not updated frequently, and it helps you creating the best possible scan for seeking those selective values. And the other thing here with us from SQL Server 2000, yet still not used frequently. These are indexed views. Remember that in Power BI semantic model, you can create aggregate tables, and aggregations can speed up queries even more than indices. There is practically no limit how much you can speed up queries with aggregations, because think of it, if you have, let's say, 1 million rows per year, and you have to combine sums for 2 years, you have to read 2 million rows. If you have pre-calculated aggregates, you have to read 2 rows only, which is approximately 1 million times faster. You could also use this indexed views besides aggregating the data also to reduce number of joins if you have some non-efficient joins. Unfortunately, as I said, this is not very well known, not frequently used. So there are also many limitations when these indexed views can be used and when SQL Server uses them automatically instead of going to the source table. So I definitely recommend you to check the documentation before you implement them. But you will see there is no need to change the reporting queries. So let me go to my demos, and I'm starting with AdventureWorks DW 2019 database and check the suffix column from dim customer. We have 3 juniors and we have 18,481 people without suffix. So let's show the statistics, show also the execution plan for this simple query where we are searching those 3 juniors. And what we see is in the execution plan, of course, we did the full clustered index scan, and we had nearly 1,000 logical reads. So let me create a filtered index on dim customer using suffix column where suffix is not null. And let's recheck this query that is searching for juniors. Now we can see that we have indexing and then key lookup. And let's see the number of reads. So we have altogether 11 logical reads, approximately 100 times less than with full scan. Of course, if we are searching for those that are not juniors, we still get full clustered index scan with nearly 1,000 logical reads. So let's drop this index and go to indexed views. Let's say I'm using this kind of query to aggregate data from DB of Act Internet Sales over product key, group by product key, and then calculating sum of sales amount and count of number of rows using count big. This is something that is necessary for indexed views. One of these limitations, count just doesn't work, but with count big it works. Count big returns big int as a result. So we have this aggregate over products. We get 158 rows, as we can see here at the bottom, and we have 1,200 and more, 1,249 logical reads, and in the fact table, and we have clustered index scan with hash match aggregate. So let me create a view, sales by product, and I actually copied the query for view definition, the query I used. So aggregating sales amount and number of rows over product key from DB of Act Internet Sales. Please note that view was created with schema binding. Now this view must be updated when I index it. It must be updated automatically by SQL Server, so SQL Server cannot allow changes in the source tables. Otherwise, it would be impossible. We would get errors when SQL Server would need to update the view. Let's now create unique clustered index on this view on my product key. And look, now I'm executing query with aggregates. Remember, this query could come either from Power BI or from some report in a line of business application even, or from reporting services report. So query is not changed at all. Yet, if I can see check the execution plan is completely different. I got clustered index scan, and this is my view scan. And what I get here is 2 logical reads. So more than 600 times less than in original query. And this is, of course, very impressive. Looks very nice, but it's always there is a catch. It's not that simple. As I said, there are many limitations, but also which aggregates do you create? I mean, in a data warehouse, you have so many possible combinations of values of input attributes and hierarchies. So it's really hard to decide which aggregates to create. You do not want to bloat your data warehouse. Definitely, you create those aggregates for queries that are executed frequently, and those aggregates that are made up from many source values. If an aggregate consists of a single value, then it just blows up the database. It doesn't help in performance. Okay, so these were indexed views. Now, data compression. Since we are in the environment where we have read mostly, write infrequently activity, we can use data compression. In SQL Server, we always had variable length data types. Var decimal data type was added in SQL 2005, and in year 2008, we got row and page compression. And with 2008 R2 in 2010, we got Unicode compression, which is very cheap, added automatically if you turn on row or page compression. Row compression simply means that every single value, even if it's fixed with data type, it is stored in a variable format. This could be also useful in transactional scenarios, since you have smaller tables. Use less disk space, reads are faster, but yes, before you update data, it must be uncompressed, then recompressed, so updates are slightly slower. Row compression cheaper than page, and so on. The better the compression, the more the overhead it has. And let's see what does it mean and how much do we get from these compressions in a typical data warehousing scenario. I am creating a new table, internet sales, using a couple of columns from default fact internet sale, and I'm inserting the data in this table. So I have I even don't need execution plan now. And I have original 60,000 and something row. So I have a result 3.2 megabytes. This is the result for data. I have no indexes. This is just index allocation map pages. So let's rebuild the table with data compression is row. And let's see what we got. So we have reserved only 1672 kilobytes, nearly half less. This is already quite impressive. Now, page compression is even more advanced, and let's check space used here. So now we have only 1 megabyte, or approximately 3 times less space reserved than we had initially. And this is already important for reads. And since in data warehouse we have most activities reading the data, then compression might be very, very useful. Next thing that is extremely important is to write efficient queries. Please understand that you can write more efficient queries than Power BI query folding could do. You can even write more efficient queries than artificial intelligence, Copilot, ChatGPT can do. I will start by things that should be already known, right? If you are just 2 small examples. If you are using self-join for calculating running totals, this is completely wrong, because using self-join for running totals gives you quadratic complexity of the queries. So, of course, you should use window functions. Now, I guess, since we are in the SQL Server track, I guess the majority of you have been here during previous Uwe's presentation, where he has shown how you can use apply operator together with partition function to get nice efficient query to find maximal value per partition. Well, apply operator is one of those that is overlooked by artificial intelligence and could be useful in many other scenarios. I will show another example, somehow similar to Uwe's example, yet more like practical without partitioning. Let me just mention something. In these examples, like self-joins or not using apply operator, the queries are even worse than queries with cursors would be. So cursors are not always that bad. Cursors are slow, but they are linearly slow. Definitely self-join, which is a quadratic algorithm, quadratic complexity, cursors are very, very quickly faster. And apply is basically some kind of cursor. Apply is for each loop inside SQL Server. So it means you apply tabular expression on the right side for each row from the left side, from the left input. So it is actually for each operator. These are examples where row-based queries are more efficient than set-based. So let me show you a couple of examples. By the way, let me just mention that I have also some more advanced presentation about this writing efficient queries with helps of helping rewriting queries, help of mathematics. Many things with help of mathematics can be done very efficiently. For example, calculating skewness, kurtosis, calculating exponential moving average. These are all examples where it's possible to write much better queries than Power Query can do, than artificial intelligence can do. Let me go to running totals, and I am doing here first in a common table expression. I am selecting in this case 3,500 rows, and I'm using customer key, sales amount over order and line number, and gender, which I will use for partitioning. I use this subquery because I can play with filter, so include more or less rows. So I will not change this. I will go through this only once, but if you want to play, you can play later with this code, and you will easily notice that if the subquery returns twice more rows, then the whole processing time goes 4 times up. 3 times more rows, 9 times up, and so on. So it's quadratic algorithm. Of course, now in the outer query, I'm joining the result to itself. So first partitioning by gender, and then order line number from the left must be greater and equal to order line number from the right. Now first row from the left will join with first row from the right. Second with first 2, third with first 3, and so on. In average, each row will join to n divided by 2 rows from the right, if I have n rows. Since I'm doing this n times, the complexity is n multiplied by n divided by 2, so it's n squared divided by 2 quadratic complexity. And you can already see that for this 3,000 and something rows, it takes a couple of seconds. Now with inappropriate filter, remember I have 18,000 rows here. If I would try to do self-join on 18,000 rows, it would already take me like 3-4 days. So here it was, I can already see here, 12 seconds. Definitely this would be better with the cursor, but it's even much easier and better with window function. And before that also, it's not just time, we can also check the statistics IO. So we have 46,000 and something logical reads in word table. Of course, this number also goes up quadratically with number of rows you are using. So let's use query with the window function, and we see that we got a result instantaneously back. less than half second. And of course, we only scanned fact internet sales table once. So very, very efficient, and with more rows, of course, the difference would grow quadratically. Now let's show you another example of apply operator. It's interesting how Uwe came to the similar problem. I'm creating now internet sales table again, just this time I'm adding country name directly to the table, country name. And I am filling it with data. This time I'm joining internet sales to dim customer and dim geography to get also country names. And I'm creating optimal index for my problem. I will search for last order date per country. So country name, order date. And I will create a small table of countries with a single column country name and insert distinct countries there. So I have 60,000 rows in internet sales, and I have 6 rows only for each country. Now let's go again with statistics.io in statistics time, and of course we would try with general query, group by, country name, max order date, and let's see what we got. So what we get is our covering non-clustered index scan, right, and then stream aggregate, but still I had 325 logical reads and quite a lot of CPU time, elapsed time, okay? Now, I describe the problem. I have text file where I describe the problem, table, internet sales, how many rows it has, and countries, and all of the structure. And let me just copy paste this to Copilot, and let's see what kind of solution will Copilot suggest. Of course, the same solution we already know. Max or country name, max order date, group by country name. So we didn't gain anything from Copilot, it's still the same. Maybe we can try to start. Now, what is the idea here? I got 6 countries only. I got an index. Let's say that index has 3 levels. So what I would expect is 3 reads per country, right? That's it, 18 reads and maybe some scan through countries, 18 pages from internet sales, and maybe 2 pages from countries. Let's see if a join managed to force starting from countries. Not really. It actually just created a little bit more complex query. Again, we did scan of our covering index and stream aggregate and then join over countries. So still we have a full scan of our index. And let's do this with apply. And of course, suddenly apply and top, suddenly we have extremely efficient query. Look what we have, exactly what we expected. 6 times 3 logical reads in internet sales, plus 2 logical reads from countries, 20 logical reads. Look at CPU time, 0 milliseconds, so simply less than half millisecond for this second query. And again, also for this query, cursor over countries would be faster. Definitely, this is interesting. So you have to know what you are doing, not always forcing some kind what people call set-oriented solution. By the way, this is an oxymoron. There is no such thing as set or row-oriented. It's just good or bad. What does it mean set-oriented? If you use apply, it's set-oriented. If you use cursor, it's not. It's bullshit. In both cases, you are doing things row by row. Anyway, let's continue with our presentation. And columnar storage. Yes, this is probably the best thing for data warehousing that is also used for querying. It has even better, you will see much better compression than page. Remember, with row, we got about 50% of saving, with page, nearly 2/3 of saving. Now here we will see that we will get even better compression rate. Of course, it means that updates are slower. Basically, updates for columnar storage do not exist. So first we do this partition data simply by splitting data into groups or segments, where each has about 1 million of rows, and then we do compression, store each column separately, column by column, and compress data using all kind of compression algorithms. So first is we use bit packing. This is similar to row compression, just that not on byte level, we go on bit level. So even like integer, like I don't know, number 5 doesn't need to use 8 bits. We can compress it to 3 bits only and so on. And then we do something similar as page compression. So we do some dictionary-based encoding and value-based prefix encoding. Dictionary means we are searching for common substrings in text or binary data. Prefix is the same thing, just for text data, just the suffix substrings are on the beginning of the string. But it's different because it can also handle numbers and dates. For example, if you have numbers 1000, 1001, 1002 in your data, then you can store prefix 1000 and only numbers 0, 1, 2 in the data. Since we have more cases, more rows in dictionary, page compression works on page level. Here we have dictionaries built on 1 million rows, and there is also a global dictionary. Also, this compression is better than page compression. And we have some reordering of rows, so we get at least partially sorted values for every single column. So we can also use run length encoding, meaning if a value is repeating like 10 times, we can store it only once and then number of repeats. But then another value, then the same value can repeat, value A, let's say, 5 times more, and it's written once again. We don't, columnar storage doesn't guarantee total sort, okay? And then we have even, finally, archival compression, LZ77 algorithm using 64 kilobyte sliding window. This is simple algorithm working on stream of bytes, checking which bytes are repeating. Now, let's see what we get with this columnar storage. Remember, this is the same storage as Power BI is using. This is the same storage. So let me create my internet sales table, and I will start by unique cluster at index, and now I am inserting the data. Please note that I'm doing this 30 times, so I will have 1,800,000 rows, not 60,000 rows only. So now I will create cluster at Columnstore index on our internet sales table. So now first, this is reordering rows, splitting data into segments, and then storing column by column, and doing all of these compressions. So let's check what is now reserved. So now we have 11 megabytes reserved. So you see, with 30 times more data, we got let's say approximately a little bit less than 10 times compression compared to original one. Now, archival compression must be added manually, and I will rebuild this with data compression equals Columnstore archive. And let's see what happens now. And remember again, I have 30 times more data than originally. Now I have 6 megabytes of data. Original data would take like 90 megabytes. So I got 15 times compression. Microsoft says that you can count on approximately 10 times compression. I got this even better, but this is because I have maybe run length encoding too good to be true. Remember, I repeated the same data 30 times, so I have more values than that are repeating compared to original data. But the price is that columnar storage is now read-only. Now we have data warehouse. We need to insert new data in, let's say, this nightly ETL job. And maybe you heard that you can update columnar storage. Well, not really columnar storage. How do updates in columnar storage work? When you insert the data, the new rows are inserted into a data store, which is a row store. And when you delete data, if this data is in some row store, data store, then it's really deleted. If it's in columnar storage, then it's just marked with a flag, and then select simply skips these rows, this data. Update, it's split into insert and delete, and then the same process happens. And merge is split into an insert, a delete, and an update, and then update split more into insert and delete. You can imagine that you get less efficient compression, less efficient queries if over time, if you have more and more rows in data store. So apparently you need somehow to maintain this. And how is it done? So we have these segments of approximately 1 million rows. When data store reaches 1 million rows, it is closed. So what does it mean? Closed means it doesn't accept new rows. And then we have background process that is called tuple mover, which converts closed data stores to column segments. By default, it starts approximately every 5 minutes. Of course, you can also start it with alter, index, reorganize, or even rebuild. Anyway, if you have these updates, if you allow updates on your columnar storage, no matter of tuple mover, it is also recommendable that from time to time you clean up things by rebuilding the columnar indices. So you rebuild also the global dictionaries, you get rid of those rows that are marked as deleted, and you get more efficient indexes. So trickle insert, row inserts go to an open data store. Bulk inserts, if they are less than 100,000 rows, they go to an open data store. If they are larger, then they are directly converted to columnar storage. Please note that the limit is around 100,000 rows. It is 10 times less than the few that we have in default row segments, 1 million rows. So it means that also these segment dictionaries are not so efficient. Another reason that from time to time you rebuild columnar indexes. More data stores means simply less compression. So as I said, it makes sense to maintain these indices from time to time by rebuilding them or at least reorganizing them. Let's see this internet sales. So I have now 3 segments, 3 row groups. I check these Columnstore row groups, which are all compressed. 2 have a smaller number of rows, but 1 has this the maximal number of rows, 1,048,576, and you can also see size in bytes. Now, why don't we have this in a single row group? Probably it was easier to split the data based on this row rearrangement, how data is sorted, so there is less overlapping of values between these segments. This is so not all segments go to this maximal 1 million rows. Now let's insert 60,000 rows more and see what happens. So what we have original three compressed row groups, and we have a new one that is open with my 60,000 rows. And I have for this, I have delta store hopped ID, heap or balanced tree ID. Please note also size in bytes. It is already, also, although I have only 60,000 rows, size is already bigger than all the other three row groups. Now let's insert nearly 1 million rows more, 16 times from my original internet sales. And let's see what happens. Still, I have a single open row group. The number of rows is less than maximal number of rows per segment. So let's insert 60,000 rows more. And see what happened. And now you see I have one closed, you see, one closed row group and one open with rest of the rows that didn't fit in the first delta store. So it is closed, and now we would need to wait for tuple mover to compress this segment. Now let's insert 120,000 rows. Insert select, of course, is minimally locked if, okay, your recovery model is simple or bulk locked. And let's see what happened. Now I see that I got compressed new segment with 120,000 rows. Please note that also my closed row group is now compressed and original is tombstoned or marked for delete at some point asynchronously. So we can keep the tuple mover with alter index reorganize, which is pretty slow. I usually simply prefer to use rebuild in night jobs. And this one actually still leaves these tombstone groups. Those that are alive are all compressed, and I have one small which is open. Now let me rebuild everything. Now I will completely change these segments, build those segments again, do row rearrangement again. Of course, it takes more time since there is more things to do. And let's check now. Now we see I got 4 row groups. You see that different numbers of rows because of row rearrangement. Again, splitting row groups was done in such a way that values are not overlapping as much as possible. And I got 4 compressed. One has maximal number of rows. All row groups are compressed. Please note that now I use like approximately twice as much bytes in size. Why? Because I rebuilt with data compression equals Columnstore, so I got rid of archival compression as at 7.7 algorithm, just to show also this difference on a row group level. Okay, so this was nice. Before I continue, I just want to refer again to Uwe's presentation. Remember when Uwe talked about issues with columnar storage and table partitioning? Yes, this is very, very unpractical, but you see, in a data warehouse, you can use also partitioned views. Manual partitioning. What does it mean? You do table partitioning because of different reasons. In transactional scenario, You do table partitioning because probably you want to have different schedule of administrative tasks on different partitions. So you might have a single partition in a single file group with hot data, data that is updated frequently, and then you might have some other partitions with stale data, data that is not updated anymore, that doesn't change, and it is in different file groups. So since you have a lot of data, you cannot afford to do regularly DBCC check DB or full database backup. But since you have these file groups, and big file groups are inactive, then you can do these actions on file group level. So you can do DBCC check file group, and then of course you can do this frequently on the hot small file group, and less frequently on read-only file groups. And then you can also back up file groups. And of course, you can also back up hot file group, small file group more frequently. Now here in data warehousing scenario, we don't need to use multiple file groups. We don't need to have different schedules for different file groups for checking the data, for backing up. So we can simply create multiple tables, and then we can truncate, let's say, just the last table, which is now kind of last logical partition, bulk insert the data, and have immediately stored it in columnar storage. And then we have a view that is connecting everything to a single logical table by unioning all rows from these partitions, which are now separate tables. This makes no sense in transactional scenario, since, as I said, you use partitioning also because of different administrative schedules, administrative for tasks, different schedules for administrative tasks per file group. Here, things are kind of simpler. Now, remember I said I have this compression. Maybe it's slightly too good to be true, slightly too good compared to real life scenarios, because of course we have data that is repeated 30 times and more, since I inserted the same data more and more times. Now, how does column cardinality influence run length encoding and compression? I will go back to these tables very, very soon. I will just show you the code. So I will compare options. I have unique integers option, I have unique GUIDs, and integers with big cardinality and strings with small cardinality. And then we will see how this cardinality influences row compression, page compression, column store compression, and Columnstore archive compression. So I'm creating these 4 tables, which will have each table just a single column. And we'll have integer, unique identifier, third integer, and then varchar 10. So let's insert data into unique integers. So I'm creating 1 million rows by selecting 1000 from dim customer and cross-joining them to dim customer, and then just storing row number from 1 to 1 million. So I have 1 million unique integers. Now, GUIDs, I will just select new ID, and I will have again the same 1 million rows, because I'm doing this select based on unique integers, right? From unique integers, just that I'm selecting GUIDs. And now high cardinality integers. So you see our big cardinality integers. I still have a lot of unique values, not 1 million, but I think 20,000 divided by 50. And small low cardinality strings, I have only couple of distinct strings. So let's create clustered indices on these tables on our column 1 and check how many distinct values I have in them. So I have 1 million unique integers, 1 million unique GUIDs, 20,000 big cardinality integers, and only 5 low cardinality strings. Now I can check the compression savings. So for example, on unique integers using row compression, I can use SP estimate data compression savings and then check what was the saving. So this is original size with requested compression. So for unique integers, I got after compression, I got only 15% less data. And I can check the same thing for page compression for unique integers, and then do the same thing for unique GUIDs, row and page compression, and then of course big cardinality integers and small cardinality strings. And instead of checking this row by row, I can go here where I joined everything, grouped everything in a table, so we can easily see what happens. So unique integers, if we look at row and page compression, we got in both cases for unique integers approximately 15% of savings. And then for unique GUIDs, you see, this is original size. Of course, GUIDs are bigger than integers, nearly 25 kilobytes. Look after compression. Well, GUIDs are very, very bad for compression. So after row and page compression, the size of data is even bigger than before the compression. And then if we look at the big cardinality integers, right? We have up already getting compression nearly 50%. And small cardinality strings, right? What about small cardinality strings? Well, row and page compression even don't work that good as with integers. So it's not very, very, let's say, attractive result. So let's check what happens by creating columnar storage. So I have this original size, right, or data size, and now I'm creating Columnstore index on unique integers without archival compression, and I can check size after the compression, and I can check what was saving. So I got, even with these unique integers, I got nearly 80% of savings. What about GUIDs? I could check the same thing for GUIDs and check what happens after the compression. This is not completely deterministic process, so sometimes numbers can differ slightly, but it doesn't really matter. Look, compression rate better than with row or page compression, but still far from anything impressive. What about big cardinality integers? Now values are already repeating 50 times. Of course, now the compression is practically 10 times, 10% of original space. What about small cardinality strings? Let's check small cardinality strings. Well, this is really, really impressive. From original size, we got like 0.1% after only 32 kilobytes. Well, values are only 5 distinct, so we have to store just 5 distinct values and the number of times the frequency of these values. So if I go to summary here, of course, again, I can see that this is extremely impressive with small cardinality strings. Still not very impressive with GUIDs. Already we got this 10 times with big cardinality integers. And now what is left, one more thing, of course, is LZ77 compression. So we start by regular Columnstore in the storage without LZ77 compression, and let's see what additionally on the top of columnar storage we got with columnar archival compression. So I'm just changing the compression level of columnar storage. So with unique integers, I got another 9% of compression additional on the top of what we have here. So we have like nearly 5 times, 4 times, more than 4 times compression. We got additional 10% with Columnstore archive. Let's check if we get anything additionally with GUIDs. And you will see again, nothing. So GUIDs are really killing the story here for database, killing the story. And what about big cardinality integers? Remember that still I have values that repeat 50 times. So yes, again, it works. Run length encoding works. Also these bytes, LZ77 works very well since stream of bytes is repeating. So we can get additional compression. So you see, without archival was 2 megabytes. With archival compression, 9 times less, 8 times less. So we got 0.92% additionally. What about small cardinality strings? Remember, we already had 32 kilobytes only here. So yes, as we expected, there is no possibility to gain anything from here. So small cardinality strings are left with the same 32 kilobytes. And yes, definitely GUIDs are the worst in every single scenario. Now, the nice thing in SQL Server is that you can measure all of these things. It's much easier to do this in SQL Server than in Power BI. But remember, all of these numbers are the same. Basically, in Power BI, you always get archival compression. You even don't have these 2 different levels. But all of these things are true also for Power BI. So what does it mean? Do you need to change your data to get smaller cardinality? Well, I mean, first, you store data based on your business needs, right? But if you always, let's say you have some attribute which has many distinct values but has some hierarchy, and you always look on these hierarchy levels, never on these small distinct values, it makes sense to group data already in your ETL process to make this data with low cardinality, values with low cardinality, and then also columnar storage will be more efficient. GUIDs in general, they really do hurt database a lot. Okay, we are coming to the end, but we have 7 minutes, so I just wanted to show something additionally. So I will just show you one Power BI report just to give you the idea of what do GUIDs do also to transactional systems, not only to data warehousing systems. So I have another presentation which is more focused on transactional data. And I will just show you the results. I will not even go to details, but just show you the results. What is the impact on transactional data of page, row compression, and GUIDs? And here, of course, I measured different things. I measured mix of selects, inserts, updates, and deletes. And of course, you can imagine that with compression, selects are faster, but inserts, updates, and deletes are slower. But the impressive thing here is what is the impact of GUIDs. Just give me a second until this Power BI report loads. So I have measured different things like CPU time, elapsed time, logs, reads, writes. And we have here on the left side will be possibility to select of the measure, and default is sum of CPU time in milliseconds for different actions, as I said, insert, update, delete, select, mixture of this command. This Power BI is becoming bigger and bigger. Power BI desktop is now, since it's so full of features, second slowest application on my virtual machine. Only SQL Server Management Studio opens even for a longer time is opening. So CPU, as we expected, row and page compression have quite an important impact. But if you have a lot of CPU, no problem. What about reads? Of course, since we have compression, reads are more efficient with page and row. Elapsed time, not big difference, but of course, without compression is faster. Write, practically no difference. Logs, really minimal difference. So CPU time was the most problematic, but look at this here on the right side. I have a filter compression type. Let's check this filter. And I can also include GUIDs in the picture. GUIDs without compression. Comparing table, same table, just GUID edit. Now look how report changes. The CPU time, it's like one blah blah blah, so 1 million something, and here with page compression it's even hard to get it, it's so small, 3000. So it's like 300 times more with GUIDs. Sum of reads, look, it's again like this time might be 100 times more. Elapsed time, writes, okay, writes we don't have much influence. Logs, even logs, how many more logs do we have if we use GUIDs? So just to mention, like GUIDs are really not appropriate for SQL Server database. They are even much worse in transactional scenario than in data warehousing scenario. Okay, so we are coming to the end. Let me check the chat if we have